We look at problem 1. To determine the shear stress for a Newtonian fluid with a velocity distribution v equal to 3xy squared minus 4x cubed I plus 12x squared y minus y3j. Show proof that the fluid is incompressible. Right, so here we need to find the shearing stress for a fluid here, Newtonian fluid. So as you know, what is the difference between Newtonian fluid and non-Newtonian fluid? So velocity distribution given here v. So here, yeah, velocity distribution means you can see here it's a ball, right? Ball v, and then we have a I ball, j ball here. So you know that it's a vector, right? So this is a vector. So this is a velocity vector equation. So let's see, which has direction I and j. So you know that in Cartesian coordinate, I and j means the x-axis and y-axis. So this is roughly the right. So this is a vector v, right, of the velocity on the x-axis, right, plus the velocity on the y-axis, right? So that's right. So this what it tells us. So we need to find the shearing stress for this Newtonian fluid. So shearing stress for this Newtonian fluid. So we have been introduced to that from your previous class, right? So because there's a formula for shearing stress. Next, we will go back to your slides previous week. Right, so this shearing stress here. So this is a shear stress or a shearing stress. So this tells us the stress on the skin of the fluid volume. Is in terms of the viscosity times the partial u, partial y plus partial v and partial x, and so on. This for a shear stress for this x and y and z. So and to make it clear to you, I mean, all in all, yeah, it's the picture is like this, right? So the shearing stress is on the surface, right? So yeah, so bear with me. I mean, this arrow here is on this surface. There's a shear stress. So there's a shear stress on that surface. So the arrow here is not within this cube, huh? So it's on the surface on that, right? So and the blue one here is on that surface there, right? On the back of this cube, right? So this cube is just a very infinitesimal volume inside the fluid. So imagine that we just take like a cube, very small one, and then we're just going to see what is the force that affecting a cube, a very small cube inside the fluid. So this is what they argue that within that the fluid there are several forces which is acting on the cube, the frontal and the back end of the cube is the normal force. We got pressure. Absolutely, there will be pressure gradient, and with pressure gradient, we have a normal force which is acting perpendicular to this direction of the axis. So yeah, we'll focus on the shear. So what is shear? Shear is actually the force on the surface force, right? So imagine that this cube is part of a moving fluid. So obviously this cube will touch the other cube as well of the other fluid. So you tend going to have that force on the surface. We call that a shear force. right? And to cut it short, the shear force, the shear stress, sorry, the shear stress is defined by this, right? So with the shear stress on the surface x and y, and the shear stress on the surface yx is equal to this viscosity times partial u or partial y plus partial v and partial x, and the shear stress on the surface xz equal to the same as the other if it's symmetry, so it's partial w plus partial x plus partial u partial z, and so on for the other surface. So this is what is given to us, and you notice that you have seen this formula before in your solid mechanics actually, which is yeah, uh, the same principle they apply for a solid material. But here, yeah, we apply to a fluid. Yeah, for viscosity, the viscosity notion here. Okay, all right. So, and you notice here, u and v is a component of velocity of a fluid, right? So u is the velocity in the x direction, v is the velocity in y direction, and w is the velocity in z direction. Okay, so we get back to the problem. To get back to the problem. So what this problem says, the problems determine the shearing stress for a Newtonian fluid. Obviously, I mean, you're in fluid mechanics 1 and 2, we solve Newtonian fluid, right? So where we can apply the F equal to MA perfectly. And given here that the fluid with a velocity distribution V equal to this, some formula 3xy minus and so on, which is, yeah, like I said, this actually means that V, this is in the velocity in u, velocity in the x direction, and this velocity in y direction. So show proof that, and also this is another question. He show proof that fluid is incompressible. So we focus on this, finding the shearing stress. So it means that we can use the formula we have seen from the previous week, the shearing stress on the surface of the cube to find this the value of the shearing stress here. So that's what we're going to do. We apply that, and we just yeah, the shear stress equal to the partial u over partial y and partial v over partial x, right? And you know that u is in terms of this formula and v is in terms of this term here, so you can differentiate that with respect to each variable, and we can solve for the shear stress. So that's what we're going to do there. So it's just straight. So shear stress xy on the surface xy and yx is equal to the viscosity partial u partial y. Oh, yeah, please record this. I forgot to press the record button. Right. And partial v per partial x. Again, what happened here? Okay, so, and you know u is in terms of that. U is 3x y square minus 4x cube. So partial u over partial y will equal to Right, so 6xy. Okay, what's going on here? Yeah. Right, and so I think, yeah, you know the drill. So just solve for the derivatives, partial v over partial x. Okay, so as well. For xy. Oh, okay. Yeah, what happened here? Right, so yeah, and then you just solve that. Put it in here. Right, so 6 plus 24, so we have 20 viscosity xy. Something wrong here. Okay. All right, so I hope you can get this. So that's 30, yeah, mu here, xy. Uh, okay, so there you go. So you have the shear stress for Newton for this velocity v, right? You know the surface xy and yx, right? And looking at the formula, other formula as well, you have a t, yz, and okay, right. So shear stress on the surface yz, so on the other surface as well. So you have to find that as well. But yeah, knowing that you have two dimensionally, right? So just on x, y, and z. Okay, but we just solve it anyway. So partial v over partial z plus and partial w, which is velocity in the z direction, and partial y. No. Okay, shear stress on that surface. All right. So we can just so you have only velocity v here, which is in the on the y direction here, and you differentiate that with respect to z. So there's no z here. I mean, there's no argument of z here. So this will be 0, and there's no velocity in the z direction. So this will be 0. So partial. So the shear stress for yz will be 0. Right. So maybe you try to solve for the. Okay. Try to solve for what is zx. Something wrong with my pen here. I need to change it. Okay, so partial the shear stress for the zx here is from the formula is w over x plus u over z. Right. So what do you think the value here will be? Right, so anyone? The value for this? So this the derivatives of the velocity in z direction over the derivatives of over x. So if you have a w here, so this should be actually here, right? So but now because the value for the velocity for w here is 0, right? So w is 0. So you have a w here 0. So if you w 0, so if the derivative of x, this will be 0 as well. And this velocity, so u, this is z here. So u, the velocity u, the reshape with respect to z. So there's no z variable there, so this will be 0 as well. So the shear stress on the z x surface will be 0 as well. Right, so that's all the shear stress for this fluid. Okay, so any question on this?
Excuse me, Doctor.
Yes.
The question asks to prove that the fluid is incompressible. Does it mean that we have to show that shear stress equal to 0? Is that how we prove?
No. So that's another question. So we just on the first question determine the shear stress also.
All
so
right,
that's on
understood.
the second question. Okay. All right. So I think yeah, this is understandable, right? It's a direct use of the formula given. So I think some of you haven't seen the formula before. So I thought because I thought you have seen this formula in fluid mechanics 1 for the shear stress for a fluid. Okay. All right, so now we move on to solving the next question, which is on the show proof that the fluid is incompressible. Yeah, so show proof that fluid is incompressible. So to remember we'll get back to our slide previous week. So from continuity equation, what happens if the flow is incompressible? So if flow is, okay, we got to the continuity equation. Okay, so we use this one. So continuity equation. Right. So this in the vector form. Okay, yeah, this one. So in this continuity equations. Right, so this from the conservation of mass, and you know that the end of the the equation would be in terms of this formula. So you have a density in velocity with respect to x, v with respect to y, w with respect to z, and then the change of density. So if it's a steady state, which is all variables are the same, or the value are the same with respect to time, so this term will be 0. No change with respect to time. We have this the change of density equals 0. And if incompressible flow, which means the density rho is constant, so means that the change is partial rho here. You can pull everything the rho here out from this equation here, and you just end up with this partial rho partial x plus partial v or y plus partial wz equal to 0. So by this continuity equation, so if a flow, I mean you have a flow velocity, flow distribution, flow equation, if you differentiate that flow with respect to the u direction, the differentiate with respect to x, and the y direction velocity, differentiate with respect to y, and the velocity of w in z directions is differentiate with z, it will always equal to 0. So if your flow profile, you apply this derivation, if equal to 0, then it's only incompressible flow. So this what we're going to solve the problem. So we're going to apply this derivation, and let's see if it's equal to 0. If it's equal to 0, then it's incompressible flow. Okay, that's our strategy there. We'll get back to the problem. Okay, so we have to show proof that the fluid is incompressible. So what we're going to do, so we're going to apply that derivation, so partial u, partial x, plus partial v, partial y, and partial v, partial w, partial z, and let's see if that equals to 0. So, and we have only it's two-dimensional, so we just partial u, partial x plus partial v for partial y, and see that it will equal to 0. And you know all the formula for u and here and v is here, so we just differentiate that with respect to x. So maybe you try that one out. Let's see if you just partial u partial x plus partial v, this term here, differentiate that with respect to y, can equal to 0. Let me try them out. So right, and so you just differentiate that with respect to x. You have a 3y square minus 3y square minus 12x square plus 12x square. Right, so looks like it's equal to 0, right? So very good. So means that is incompressible. And also a steady state, right? So it's a steady state because it doesn't the equation, there's no changes, there's no variable for time. It's just location here, t3 y x. So there's no time, there's no t here. So this, you know that it's a steady state. So it's a steady and incompressible. And the steady state. Okay. All right, so any question on this? All right, so no question. We move on to next one. Okay, so problem 2, two-dimensional velocity field of an incompressible Newtonian fluid described by here velocity v here. So ij, where velocity has units of meter square and xy in meters. Right, so determine the stresses. These are the normal stresses, the x and plus on the surface of x, surface of y, and the shear stress xy at the point x, 0.5 and y equal 1 meter if pressure at this point is 6 kilopascal and the fluid glycerin is 20 degrees Celsius. We show the stresses on the sketch. All right, so yeah, and given, so these are the formula given. The formula is given to you that the normal shear stress given by here, the negative P plus the 2 shear stress plus U over X, and given okay here. And so this is the shear stress, yeah, which we have used this formula on the last problem. Okay, so this is yep, apparent stress at the point X 0.145. We have to find this normal force there. So we make use of the formula given and we solve problem at that particular point. So we just substitute the values inside the formula. All right, so let me pull up. Hold on first. Where are we? Okay, so yeah, we have to solve the normal stress and the shear stress at a given point, right? So given point at a specific point, 0.5 and 1 meter. So 0.5 and 1 meter. So means that we have to use this formula here, apply this equation inside here. So because this is representative of u and v, differentiate that with the x and then you substitute the point there. The x will be 0.51, so you get a value, right? So straightforward substitution and solving the problem. It's not working. Right, so we want to partial u or partial y. But partial x equal to 12y squared minus 18x squared. And then you substitute the value for the point. Right, so for the point will be 0.5 and y. Right, so this so 7.5, right? And given the pressure is 6,000 Newton per meter square given by the problem, and the viscosity is so viscosity here you have to get it from the table in the textbook. So for in this case is 1.5. Liters second per meter square. Right, so now we can put it into the equation. Right, for the equation given the normal shear stress, so it's negative P, yeah, plus 2 partial U and partial. Okay. Okay, pardon me about this, huh? So this partial U, partial X, sorry. So, and you put all the values there, right? So negative 6,000 plus 2, 1.5, and that's 7.5. So what do you have? for about negative 5.982 Pascal. Negative 5.98 kilopascal. Right, so that's right, so that's how it is. So it's a direct use of the formula. Right, so we use the formula here. Right, we use the formula here, and then yeah, the partial u, the partial x here, right? So you can look at the u component of that velocity profile, and then you differentiate that with respect to x, and putting the point, the value of the point. So point is x 0.5 and y is 1. So you just put in the value. So you have the value for the partial u partial x, which is 7.5. And viscosity 1.5 here, so it's taken from a table. So based on the glycerin liquid on that particular temperature. So given by the problem, then you solve it this question. So you have this a normal shear stress on the x direction. Okay, so any question on this? Okay, so I let you solve the other part. So it's similar method. So you know the equations. So you just differentiate your velocity component and you solve it. Right. So I let you solve for the other part for the normal stress on y and the partial stress on xy. Okay, so we'll take a break, 5 minutes break, and then we'll continue back. So in the meantime, you can solve that.